welcome to my talk. I'm going to talk about security in Android. I'm going to provide a little overview of the Android platform, which you all know, but to be on the same page. Then we'll go through the attack surfaces for Android, on which security researchers will focus, and I will cover a small amount of time on web-based Android applications. So what we're going to talk about: introduction, overview of the Android platform, attack surfaces, and security in web-based applications. Who am I? I'm a student, computer science, majoring in development of secure software. Foremost Android enthusiast and developer, and I tend to blog from time to time. The talk will be not that technical. In the last part there will be some code snippets, but nothing too fancy. This presentation is a call for action, because I think developers are the front line when it comes to security. You have your system, who needs to provide security mechanisms, but yeah, you can also argue that the user needs to use his common sense, but in the end it's also the responsibility of the developer, and you don't need to be a security expert to reach some kind of level of security. So the Android platform, it's composed of 5 main layers. You have the Android applications, the Android framework, the Dalvik Virtual Machine, it's RT since 4.4, the user space native code, and the Linux kernel. So this is graphical. I think everybody saw this image already from Android. So the first layer is the Android applications layer. It allows third-party developers to bring additional functionality. It uses the Android Framework API to interact with the system. Applications are signed with keys, and developers need to generate these keys. And this key does not say that the developer is trustworthy. It just creates a trusted relationship between updates from an app. It's something you have to keep in mind. You have different application components, like the Android manifest.xml, usually generated by your IDE. You have intents, activities, broadcast receiver services, and content providers. Yeah, I can elaborate on that, but I think that's outside of scope for now. Then we have the Android framework, which is a second layer. It provides an interface for the Android applications. It allows developers to perform common tasks. You have standard and third-party libraries, like the Apache HTTP client library, the XML parser. And to give an entry point to those deep classes, you have the framework managers, like activity manager, view system, package managers. The Dalvik Virtual Machine, it's based on the Java Virtual Machine. Basically, when you implement a virtual machine, you have 2 choices you can make. You can go register-based or stack-based, and mostly you have 2 choices. Register-based means you have memory allocations through which you pass your data. Stack-based is you push your data onto a stack and you push and pop your data. It's pretty close to Java, but not quite the same. It gets interpreted into Dalvik bytecode, which basically makes a DEX file of your code, which stands for Dalvik executable. Once it's loaded on your device, it gets transformed to an optimized DEX file. It should be noted that these ODEX files are not interchangeable between devices because they use device-specific optimizations. And the first process to be started is a Zygote process. And basically, when it initializes, it uses shared core classes and libraries. It initializes these classes and libraries, and when a new process gets spawned, it gets forked of the Zygote process, and these classes and libraries should not be initialized once again. So this is optimization that Android gives to create processes easily. Then the next layer, deeper into the Android platform, we have the native code and operating system user space. It's comprised of 2 primary groups, libraries and core system service. Libraries, you have our shared libraries accessed through the Java native interface. And we make a distinction between vendor-specific and non-vendor-specific, like vendor-specific are your libraries for GPS, hardware acceleration, specific hardware like accelerometer, and then we have the non-vendor-specific, like your typical open source projects like libpng, libexif, those kind of things. Then you have Bionic, which is a BSD-C runtime library. And it's interesting for security researchers because this native code is, it's coded in native code, which is in the C language, which has memory corruption vulnerabilities, which basically means you can exploit vulnerabilities in the memory. In theory, this sounds easy. Android has a lot of security boundaries in check to prevent these things. Then we have the core system services in it, which basically initializes your system. The radio interface layer, which puts phone into smartphone. Basically, it lets you receive SMS, lets you make phone calls, gives you internet without the need of Wi-Fi. And then we have the Android debug bridge. Everybody knows the Android debug bridge, so I don't think I have to elaborate on that. Then we have the kernel. Kernel is very extensive. It's not a vanilla Linux kernel. Android did a lot of additions to the Linux kernel, so it became an Android fork. The two most important are the binder and the logger. Binder provides inter-process communication and basically is the basis for intents. I don't know if everybody knows intents, which you use to pass information through applications or activities. Then you have the logger, which basically implements 4 buffers in kernel space, like main, system, radio, event. And when you use IDB lockout, the first two, the main and system, are the default buffers you read out. So applications and system can write messages to these buffers. This is also very interesting because a lot of developers forget to get debug information out of their code. So sometimes you find interesting pieces of information inside these buffers, which could make you think about the security of the application. Conclusion, I would like to add that that Android is a very complex system, and if you look at their security architecture, is based on the principle of least privilege. Basically, this means if you have a module in your system, you tend to give it permissions as most as they need, not more, because if they get compromised, they don't have that much permissions on their own. So that's why the modern exploits we see are a combination of vulnerabilities. As an example, I took the root for the HTC Butterfly. Without going into much detail, it's basically a combination of a content provider exploit that they used. They got a file descriptor pointer, and together with a kernel exploit, they managed to get root. So, without going into a lot of detail, that's what it was. Now, second part, attack surfaces in Android. This is where the security begins. We have the terminology we have to cover. So you have an attack vector, and basically it's the methods used to carry out an attack. And then we have the attack surface, and you can see this as a target's open flank. It's a code you can execute without the need of doing much effort to get there. It's the things you look at when you try to search for a breach. We can classify these attack surfaces. We have the physical agency, agency. Yeah. English is not my mother tongue. Physical agency, local surface attack, physical surface attack, and the remote surface attack surface. Excuse me. And to reason about these attack surfaces, we use a lot of we use some properties like the attack vector. Basically, if the attack vector is what do you need to do to reach this surface? Is it social engineering? Is it some kind of other thing you have to carry out to reach this surface? This can be something you want to consider when you try to exploit things on the system. Privilege is gained. What if you exploit successfully an attack surface or a vulnerability in an attack surface? What are your privileges gained? Is it enough for the effort you're putting in? Memory safety. Is your vulnerability located in a memory safe language like Java or a non-memory safety language like C, native code? And the complexity. How complex is the code? Complex code tend to have more vulnerabilities because you have a lot more paths going through your code. So a smart hacker will try to find paths you didn't foresee to be there, but they are there. And the general rule an attacker will follow is that he will try to get as much privilege possible with as little investment as possible. Now the physical agent, yeah, this guy. The attacker is in a range of a victim, and basically your Android device supports different kinds of communication, wireless communication channels, like GPS, baseband, Bluetooth, Wi-Fi, and NFC. Now for GPS is a one-way communication mechanism. You just get data from a GPS satellite. Doesn't need to know where you are, just sends you data. You don't send data back to a GPS satellite. It's accessible through android.location.store or Google Play services like the speaker before me mentioned. Third-party libraries tend to not respect the end user's privacy about location. It's well known. There are no well-known attacks through that go through the GPS interface. The only attacks possible that a user can do with his phone are location spoof attacks. They want to have an advantage in a game that's location-based, or you want to do a check-in on Foursquare that's where you not really are for some kind of reason. That's about it. Then we have the baseband interface. It's there to communicate with mobile networks, of course. Mostly attacks that occur here are man-in-the-middle attacks. Basically, the attacker finds himself on path between the device and some station he set up maybe himself. And basically, when you use a baseband connection, the station with the strongest signal gets chosen. So if you set up a station that you control, you can make the victim trick into connecting with your station, and you can monitor network traffic, or you can even generate traffic and send it to the victim to trick him. We call this a rogue-based station attack. Now, a lot of communication in baseband is based on protocols, and it should be clear that every protocol is an attack surface, because there are protocols that are not very good secured, and but the downside to the baseband attack surface is that it's very resource intensive to exploit. You need to have a lot of hardware, because talking with baseband chips is not something you do with your normal computer. You need specific hardware. Then we have the Bluetooth layer. It's a rich attack surface, which means there are a lot of different profiles that Bluetooth use. Yeah, Bluetooth is based on profiles, like the headset profile, the hands-free profile, the FTP profile, and basically everything you can do with Bluetooth has a profile. Most of the profiles require pairing, which can be achieved in two ways. Through input of a numeric code, the devices who want to connect to each other, they have to put in the same code, and the hard-coded code. You have devices with hard-coded codes, which are the most interesting to attack because they're always the same. Possible attacks after pairing are bluejacking, blue snarfing, blue bugging. The first one, bluejacking, is not just for sake of completeness. It's just when you're paired, you're sending messages that are like you're hacked and stuff like that. It's script kiddie stuff. Blue snarfing and blue bugging is exploiting the Bluetooth interface to gather information from the device, like contacts, calendar, other types of info that are available to the Bluetooth interface. Wi-Fi is a really rich attack surface, like Bluetooth. It has similar attack surfaces as Bluetooth, but a lot more also. It's very extensive. I did not cover a great deal because there are no well-known attacks that only work for Android devices through Wi-Fi. So every Wi-Fi attack could be possible also on Android that you know for just regular Wi-Fi devices. So if you want to know that, I suggest you read up on literature because it was very extensive to put here in the talk. Near-field communication is an interesting one. Near-field communication is built on radio frequency ID, and basically nowadays it has three main use cases. Tags, basically your stickers. You write data onto it and you can read it out. Beam data to between devices. So you put devices together and you can beam without the need of some wires. You can beam your data. Contactless payments. I don't know if anybody used this. I personally didn't use contactless payments with NFC because I don't trust it and I never had the opportunity to use it. Also. So yeah, also for the sake of completeness. Now some successful attacks on NFC. Charlie Miller, he set up connections through an exploit in NFC. He was able to set up connections of Bluetooth or Wi-Fi direct with the victim's device. Joshua J. Drake and George Richard Ski. They were successful in an attack where they used NFC to perform a browser attack. Basically, they tricked the user into loading an URL that performed a drive-by attack, which I will cover later. But they tricked to install malware, basically, by the use of NFC. And then we have MWR Labs, which basically is a group. They have an excellent site. And there was an exploit in the file format parsing of the Polaris Office. I don't know, anybody used it? It's, I think, standard on HTC devices, or not anymore. But basically, they had an exploit in the file format parsing, and they used NFC to successfully exploit this vulnerability. The local attack surface. The ultimate goal of this attack surface is to get privileged code execution. As I mentioned before, the Android security architecture is based on least privilege, which basically means that you need a collection of exploits to get some level of privileges. When you attack this attack surface, when you try to reach some level of privileges, you will use code that's already running on the device to gain more privileges. This could be interesting when you want to root something, not the hardware kind of root like Adam Adler does. The file system is one of those places where you start to look. The file system in Android is Unix-based. Attack surfaces are exposed through entries in the file system. And basically, these are inter-process communication functionality, which means you can talk with other applications. So the first job of an attacker will be to determine the code behind an endpoint, which can be an interesting attack surface, a deeper attack surface, and he can choose to search for vulnerabilities. Your typical zero-day exploits, they come mostly from this layer, because you have a lot of access to a native code in the behind the entries. System calls. The kernel. When you have the kernel is responsible for handling system calls. So in an operating system, you have kernel mode and user mode. User mode is when the user application runs his code, but he has to do when he has to do a privileged function call, like for example opening a file. Then the operating system will switch to kernel mode. The kernel will do this function call because it has to happen safe. You don't want to corrupt memory locations or something like that. And basically, the switch when you have a function call and you switch from user mode to kernel mode, they call that a system call. You're calling to the system to do something. And these system calls they can handle data that you put in from your Android application. And basically, you can put in malicious data if you want, because this kernel is running a native code in kernel space. And if you want to search for such system calls, you can just download the kernel source code and Control F for syscall define. And all these functions that accept input, you can search for memory corruption vulnerabilities, which could be an interesting place, because if you gain privileges here, you're in kernel space. So it's a pretty big deal. Then, as I mentioned before, Android added his binder logic, which is unique for Android. It's the basis of intents, and it's basically implemented as a driver in the kernel. And you can write a service in native code on top of the binder, which, because you're that close to the kernel, exposes deeper attack surfaces and could be interesting for privilege escalations. Again, because you're in kernel space. Other attack surfaces are shared memory, the baseband interface, and the sockets. The baseband interface, I mean not the baseband we saw earlier, but the firmware running on the baseband chip. It's also very low level. I think this attack surface is very interesting for security researchers, because your average hacker wouldn't look here. It comes further further on. I will say where the average attacker will look. Okay, now we have the physical attack surface. Physical attack surface is a surface where you require physical touching to the victim's device. Most people consider physical attacks impossible to defend against due to the nature, because if you have a device, you can almost do anything with it, especially when it's rooted or something like that, or bootloader unlocked. So a first possible attack of the surface could be dismantling devices. Disassembling devices, this is the action of disassembling devices and attacking the very hardware. Now, hardware manufacturers tend to not protect their hardware that good, because they think in order to hack hardware, you have to have a lot of knowledge about the hardware. It's a very, the nature of hardware is it's difficult on its own, and they think that this is a protection on its own. They don't need additional protection. Attack surfaces, once you dismantle a device, are, for example, serial ports where you can read debug information, or the JTAG debug ports. Adam Adler, anybody know this guy? He does the XDA unbox things, and he uses this attack surface constantly to get root on the new devices. It's not what you do at home, at least I don't want to ruin my devices. The Android debugging bridge, this is a funny one. A lot of developers use the ADB, but they forget to disable it once they jack out their smartphone and they go for a walk or something like that. And there's an attack that they call it choose jacking. And basically, you on a conference like xda-DevCon, you put a charging pole outside, and you put your device on it. And if you forget to disable USB debugging, the charging pole can just use the ADB interface to download information from your device. Since 4.2, I think, they added authentication with RSA key pair. So now, if you connect through ADB, you have to accept the key pair. Do you want to connect with this device? And I have to put yes or no. The attack surface remote is the largest attack surface. So the remote attack surface. It can be devastating to a device because of the very nature of a remote attack surface. It doesn't require, the holy grail for attacker is basically a remote attack surface where it doesn't require user interaction to do something. That's the holy grail for an attacker. If you have something like that, then a lot of users will be attacked in a very short time. And a big part of that attack surface are browser attacks. Browsers are complex systems. Nowadays, they have to support a lot of web technologies and protocols. And all these web technologies and protocols are possible attack surfaces. An attack, the drive-by attack, which I mentioned earlier, is to trick the user to load an URL. And it will point to a website which uses an exploit in your browser and drops malware on your device. Man-in-the-middle attacks. Without crypto, I don't think there's much you can defend against it. Cross-site scripting and cross-site request forgery are basically attacks based on JavaScript vulnerabilities. And browsers enforce the same origin policy, which was called in life for the JavaScript vulnerabilities. And basically, this means that if you have a site A running inside a browser tab or something like that, and you have a site B who wants to get the contents, it has to be of the contents of the other site, and using JavaScript for it, it has to be from the same origin to access that page. That's basically, in short words, what the same origin policy is. Other attacks on the remote attack surface through ad networks, for example, or media and document processing, like I mentioned before. If you have a browser and you open an image and there's a vulnerability in the image processing library, then this attack surface becomes vulnerable through the use of the browser. If you manage to hack into the Google infrastructure, that's basically the biggest remote attack surface. I think you will be a hero then. And then, yeah, the malicious apps and third-party ecosystems like Black Market or something like that, you have to watch out for those. Now, security in web-based applications. Well, web-based application. When I talk about web-based applications, I mean the applications that use a WebView component, which is a class you can use in Android to load a website or to view web content. It's based on the WebKit web browser engine, and it's extensively used in hybrid applications. Hybrid applications are those applications you write in HTML5 and use JavaScript and CSS, and you can port it to all platforms just using Sensa Touch or Apache Cordova, something like that. And basically, it's a really quick method of developing, which I don't really approve, but for various reasons people use that. We'll see in a moment why I wouldn't use it. It's a remote attack surface, so there are issues, else I wouldn't have put this in my talk. So basically, if you use a WebView component and you don't need plugins, disable it. It's disabled by default, but it's never a bad practice to disable it actively in your code, which you can do through, is it readable, the red thing? WebView.get settings.set plugins enabled false. So you go to the web settings object and you disable it. File system access, which makes it possible for web apps to access local resources. It's enabled by default. If you don't use it, if you don't need it, just disable it. It has no business being enabled when you don't use it. And the last one, disable JavaScript. A lot of web applications need JavaScript, but think twice when you want to use it, and if you don't need it, just disable it. WebView issues, again, is JavaScript necessary? You have to make that question when you use WebView components. And basically, when you use a WebView, there's nothing you can do against man-in-the-middle attacks besides using server authentication, like OpenSSL library. Use an OpenSSL library where you have a service certificate where you know with which server you're talking. Try to do some origin checking. I will show in a minute how to do that. And only load third-party content that you trust, because I think when you develop default, then origins are not checked. You don't know if you have if you have a WebView that can basically open every web page, and you don't know which content you're loading. And there's a way in Android to provide a JavaScript to Java bridge. It's dangerous. I talked about the same origin policy, which basically means that web apps from different origins cannot extract information from each other. This is not enforced over the bridge. So one side you have your Android security model, which is based on permissions for your app. And on the other side you have your web content, which is more or less governed by the same origin policy, but these do not perfectly match up, and we'll see in a minute why this can be dangerous. Are there JavaScript developers in the room? Well, if you look at this is a very dangerous piece of code which was executable before Jelly Bean, up until Jelly Bean. And basically what this does, it uses reflection to open an app. And what this means is when your WebView executes this JavaScript, so yeah, maybe I'll start from the beginning. You have your bound object .get class. Your bound object is a Java interface that you bind to from your WebView. So basically, this is the bridge I was talking about. So you have your Java code, the bound object, with all its public methods, and basically this attack uses this bridge to access the Java runtime, as you see there, Java lang.runtime, and it gets the runtime and it executes the command arguments that are passed to the execute function. And if you look at what the argument is, it's basically a malicious app that a user has installed or something like that. It could be any command. You could be creative, I would say. And basically it lets you access the Java runtime. And okay, that's not very clear. the Java code that will be executed once this call is passed, it executes in the context of the app. So if your app has a lot of permissions, the app that is loaded through this code also has the same permissions. That's not something you want to have. I was talking about origin checking. How can you do that? You do that through resource inspection. And a first approach is to intercept page loads. And when you intercept a page load, you try to check against a whitelist of trusted parties. So you get the URL that your WebView is trying to load, and you can check if this is a trusted location on the web. In order to do that, you need to override the native methods in the WebView client. Okay. So the should override URL loading, you override it. You get an URL and you get a WebView object, and basically with the URL you can parse it using the URI clause, and you can get the host, the name, the path, and the method is documented. If you return true, then WebView will not go further. It puts the responsibility of loading the page on the shoulders of the developer. If you return false, WebView will just load the page without questions asked. So I here return true, but what you could do here is additional logic like logging, warning the user is trying to load something that's not trusted. Yeah, and there's a method URL is not allowed. This is typically the method where you implement your whitelist logic, like pattern matching against URLs or something like that. Now, what about iframes or content between script tags or XML HTTP requests? These get not intercepted by the call by the method I showed earlier, but you should override the should intercept request method. It's an example of it. So again, you get an URL. Okay, I forget the annotation. Should put @override for being complete. Then we have the if test. If it's not on the whitelist, the URL, return get resource manually, or let the WebView handle the loading of the resource. Get resource manually basically just returns a string as a buffer input stream, not allowed to load resource. It's pretty straightforward. It's very basic, but the method not on whitelist is usually a very complex method where you put regular expressions to match against a list that you control or that you trust. It's not very clear, but here are a list of useful methods. You can get the host, the name and the scheme, and to implement your logic for whitelisting. So I did an example with the xda-developers.com index.html. Get host returns xda-developers.com. Get scheme returns HTTP, and get path returns index.html. Very useful. Then the @JavaScriptInterface, it's very dangerous. Same origin policy is not enforced for the bridge. Iframes become a nightmare because these are different origins that you expect from your web content, because on iframes you can load third-party content. Hybrid software stacks use this. Apache Cordova, SensorTouch, and generic for all hybrid frameworks are fracking attacks, where you basically let malicious third-party content attack the servers and the system and access system calls they shouldn't have access to. In conclusion, it's difficult to get it right. It's very important that your pattern matching for whitelist is good, it's complete. You have to watch out for hybrid mobile apps. I'm not saying that you shouldn't code hybrid, but you have to make the consideration if security is important. Maybe it's better that you put the effort in native coding. Also, the hybrid frameworks, Apache Cordova, I think, they have a whitelist function, but default it's on allow all domains. So I don't know if anybody used this before, these hybrid frameworks. Yeah, check your domains, basically. And that was my talk. I don't know, a little bit over time. Time for questions.
What security features are there in Android? So things like depth or address-based randomization. Do any of those exist in Android?
Yes, very good question. Yes, when I talk about vulnerabilities in native code, theoretically it's possible, but when you have to go practical, it's almost impossible. That's why I said you have a collection of vulnerabilities. So some security boundaries that Android implements is Android space randomization, and also prevention of data execution. And basically, if you remember the crypto vulnerability that was exposed a couple of months ago in the key store, basically they managed to find an exploit in the Android key store. And it was very big news in all the media. But when you looked closer at the exploit, it was a memory exploit. It should be handled, but it was not something that basically should keep you awake at night. The reason why, when you inject code on the Android stack, it gets converted to a 7-bit ASCII code. It's just the way how it ends up in the stack. And for example, if you have Android devices running an ARM chipset, a lot of instruction words are not able to be formed with 7 bits that you would like to have, and you have like basic compares you can do, but not really execution of code or anything like that. So exploits exist in native code, but it's very difficult in the Android system to exploit those. Basically, it's always a collection of vulnerabilities. It should be solved.
You mentioned hardware a few times, so could you give some example of how hardware could make phones more secure?
What I would like to see, so your question was how hardware could make a phone more secure? I speak from experience now. I did an internship in the mobile industry, and my internship was to penetration test a library in Android that was that provided a software mobile key store. So basically a key store which contains private keys, but it was fully implemented in software without hardware backup. And things I noticed which I would like to see on Android devices standard are, for example, trusted platform modules. There's no way to store private keys hardware backed. There are some devices, I'm not sure, but the support is there since Android 4.3 for hardware-backed key stores, but they're not there. So this means that that private key material at some places in the memory, which, yeah, you don't want to have it, but you can do it in a secure way, but it's not the most secure way. You could do it more secure, but it's the effort that attackers should put into it, and yeah, that's sometimes the reason where there's no hardware-backed key stores. But I would like to see that in Android devices. It would bring up, it would improve the security a lot.